Hello everyone, this is a status update presentation for our fantasy football draft assistant for our DSci 591 capstone class. So the first thing I want to do is kind of remind everyone about what our project is about. So essentially we want to develop a fantasy football draft assistant which will help users draft their fantasy teams more efficiently. And so it works by providing player recommendations through analyzing the draft order, viewing the league scoring settings, and the user's team needs. It'll be able to make real time adjustments based on who's been drafted in the draft so far, as well as the user's current roster composition. So, ideally, if you have selected two wide receivers, it would want you to select a running back next. Or if you already have a quarterback, it probably won't suggest that you select a quarterback next. And finally, it will provide data driven insights by using historical player stats, expert player rankings, and a machine learning based player projection system to maximize draft value. So now I want to go over our data acquisition overview. So first we developed a web scraper to collect player statistics from Pro Football Reference as well as historical average draft position statistics from Fantasy Pros. Next, we cleaned and processed the data by standardizing player names and team abbreviations for consistency across our data frame, as well as correcting any positional inconsistencies. So, for example, in our case, we did not want players that were punters or non offensive players. And we also converted our raw statistics into structured numerical columns. After that, we calculated our derived features. Fantasy points from points was collected by calculating the amount of fantasy points a defense would have received from allowed points on a weekly basis. So, because this number would change week over week, this was not something that we could simply calculate from a total points allowed column. And so then we calculated our target variables, fantasy points scored, by applying fantasy scoring formulas for both PPR and non PPR leagues. And we also calculated average ADP and positional ADP for every player in our dataset. Finally, we merged all this together into one final dataset, which would be ready for analysis. So with that, here is what we were left with after our data acquisition. So we had player metadata and fantasy football information as well as our target variables, and these columns would remain consistent and filled out for every single row in our data set, apart from a defense not having an age. But apart from that, these columns would be there for every single row in our data set. Next, we can take a look at some passing statistics, which would generally only apply to quarterbacks, like passing yards and touchdowns. And then we have our rushing and receiving columns, and these would also most likely only be applicable to wide receivers and tight ends and running backs, because here you have things like receiving yards, rushing yards, and receiving touchdowns. And then we have kicking statistics as well for kickers, where we have columns like field goals attempted and field goals made. So now we have our subgroup, which probably had the most amount of columns, individually specific columns, and that was defense, because here we have columns like total yards allowed, rushing yards allowed, penalty yards, sacks, interceptions. So with a lot of information, we did have some choices to make as what we wanted to keep and what we didn't want to keep, and those we will address later on in the presentation.
Now that we're familiar with this data set, we're going to start now looking at the exploratory data analysis that we did for this project. We start the data discussion by looking at some of the categorical features. In particular, we look at the different positions by year here. And what we see in the plots here is that there's some variation amongst the positions, but the general order is maintained every year. We don't anticipate any issue with data imbalance because this is actually representative of the distribution of positions within the NFL. For the age of players in our data set, we tend to see a right-skewed distribution for most of them. However, we highlight here the kickers that have a relatively unique shape amongst them. What we see is that they tend towards older players and have a much broader distribution of ages. We suspect that this has to do with the unique fact of this position being less about pure athleticism and more about technique and skill that doesn't necessarily degrade as much as you age. So looking now at fumbles and interceptions thrown, we see a surprisingly subtle metric. Fumbles are bad, but they may end up being interpreted as good due to the fact that how many fumbles you have is going to be correlated with how much time you have on the ball. The more time you have handling the ball, the more fumbles you're going to have. And time on the ball is going to be associated with a bunch of positive metrics because you're a player that's being used very often, probably because you're one of the better players. And so this metric may actually end up being a positive indicator, even if it is typically considered a bad thing. Interceptions also follow a similar pattern, so it'll be interesting to see how our model ultimately ends up interpreting these results. For both rushing and receiving touchdowns, we see that there's a tendency towards having a pretty extreme right skew with very serious outliers. For the rushing, we see that the quarterbacks and running backs have a higher range of rushing touchdowns and a higher maximum, which is what we expect. That's their role. And for receiving touchdowns, we see something similar, except with wide receivers as the ones with the highest range. And that makes sense again because that's their role. For field goals and extra goals made, we kind of see an interesting bifurcation of different players. We see a normal distribution of kickers with scoring field goals, and then a very large group that has little to no field goals at all. We see something similar as well with the extra points made. In 2024, it's a bit of a difference where you tend to have fewer extra points made overall, but the general pattern holds, and that suggests that there are certain players with little to no field time, and those who are getting a lot of field time, probably because those are the better players. Looking now at defensive touchdowns and touchdowns allowed, we see a few things here. First, for defensive touchdowns, there's really no clear pattern that we can extract from a year-to-year basis. But one thing we do see, though, is that there is a tendency for the special team touchdowns to drop every year. And whether or not this is a real pattern would probably take more time to be confirmed, but it is something to note and would be interesting to track on a long-term basis. And then for defensive touchdowns allowed, we do see a somewhat more normal distribution, and it also does seem that they are allowing more touchdowns in recent years. So this is also possibly suggestive of a broader trend within our data that may continue on in the future. But again, that's something we would need more time to look at. Moving now into our average draft positions, or ADPs, what we see is that for average ADPs, the major takeaway is that kickers and defenses tend to be selected later. This isn't really surprising to people familiar with fantasy football, as that's kind of normal. As to the positional ADP, we see a really interesting situation where there's a region of competitive positional ADPs, so those are lower values, and a large amount of non-competitive positional ADPs, so the big spike you see at the end of every one of these year graphs. This is suggesting that certain players are simply performing at a higher level, and there's a lot of extras, bench warmers, or just players who are just not being selected because they're not performing at that high level that our top players are. So looking now at our target variables, the PPR fantasy points scored, we see that there's a very extreme right skew in this data set. This is suggestive of the fact that higher performing players are rarer and performing significantly better than lower ranked players. The defensive teams, their fantasy points tend to start at a higher value than most of the other positions. And this makes sense because we know that all defenses will play in a game, and that's not the case for individual players. So that makes a lot of sense. For other positions, we see again, heavily right skewed data as well. And looking at the maximum value by position, what we find is quarterbacks tend to perform the highest in terms of PPR at about 400. The wide receivers and running backs are kind of in the next tier at about 350, around that as a maximum. Tight ends doing the same for about 300. And then kickers and defense tend to peak out around 160. So this is suggestive of the fact that there's sort of a rough order to draft positions that we might actually find emerging from our recommender system. Looking now at the standard fantasy points scored, we see a very similar general trend within the standard scoring as to the PPR, with the major difference being that quarterbacks are much more emphasized in the standard scoring system compared to wide receivers, tight ends, and running backs. And that makes sense given the emphasis that PPR puts on those other positions compared to standard.
Moving on here, we can see at the bottom of our screen the non-null counts for all of the different columns for each season from 2022 to 2024. And as you can see through those counts, the null values do fluctuate from season to season, and this is based off of player count and availability, with the exception of our 32-team defenses, because they play every single game in every single season, and they don't fluctuate, which makes sense. It's important to note here that for our players, there were 970 non-null unique player names across all of our seasons, which makes sense given our data setup and the quality of our data. And we really want to take another second to explore how it's important that we understand the difference between true nulls versus true zeros. So null values aren't necessarily an error. They just represent when a player doesn't participate. And a value of 0 is also not an error, and it's not null because a quarterback, for example, could complete one pass for 0 yards where they are participating. They just didn't get a very good stat line. Now we'll move on to our outlier analysis EDA. So outliers are crucial to our recommender system as they represent high-performing players. And unlike many traditional machine learning scenarios, we are not removing these outliers because they're actually the exact type of players we want the recommender system to prioritize. Below we can see a point per reception fantasy scoring by position plot for the 2024 season that separates all the position groups. And as you can tell, positive outliers mean high performers. They're the ones scoring a lot of points. Again, these are the types of players we want to have captured by our recommender system. It's important to note that defensive teams show a smaller variance due to full game unit-based performance, as they're not individuals, but they're teams, and every team defense plays every single game. Continuing on here, we can see through these plots that most non-defensive stats show extreme rightward skew and kind of follow that power law distribution where a small percentage of the players are producing the most impressive output. And we don't really want to lose this natural element of the data because it's important for our recommender system, but we may need to potentially transform the data for machine learning to do its work properly. And we've explored several different transformations. As we can see in these plots, we've looked at log-scaled, box-cox, Yeo-Johnson, and square root transformations. And while we explored these all, we will be identifying the most effective transformation per individual feature before any final modeling is output. And lastly here in our outlier analysis, we just wanted to highlight some specific outliers that we thought were interesting. So on our left, we have a total passing QB box plot for the 2022 season, and you may see that top outlier is something that you would normally want to remove, but in our case, that's an exact kind of performance or player that we're looking for. This represents Patrick Mahomes' season in 2022 where he won the MVP and had an amazing total passing season, so that's the kind of player we're trying to capture. And then on our right, we have a really specific instance of something that might throw other people off in terms of seeing that most teams played 17 games in the season of 2022 for defenses, but there were a couple teams that played 16 games, and that actually represents a game where a player had a sudden cardiac arrest on the field and the game had to be abandoned. And normally looking at that, you might think that's a data error, but we wanted to make sure that we pointed this out and showed that we really did dig into the data and make sure that everything adds up. So that is actually an expected histogram here, which is very interesting.
Next, we tested for multicollinearity in our dataset. First, we calculated the VIF scores for 3 subsets: offensive, defensive, and kicking stats. We focused on exclusively the 2023 season for the multicollinearity analysis. This simplified the analysis as statistical relationships should be consistent year over year. Once we identified features with excessive collinearity, we dropped them from the dataset. Some examples include passing attempts and rushing attempts, as these were captured by other variables like passing completions and rushing yards. At this stage, there are still some variables with multicollinearity, but this will be addressed with feature engineering further down the line. After dropping our initial variables that were affected by collinearity, we looked at correlations between our features. We see that multiple stats within each position group are highly correlated, which is contributing to high VIF scores. Some examples of these would include, if you look over here, we've got passing yards, passing touchdowns, and interceptions thrown are highly correlated. We also have certain breakdowns of field goals made. So due to these strong relationships, we decided to drop redundant features like specific average draft position sources, certain breakdowns of field goals, and more. Now let's move on to our feature engineering and analysis. Our original dataset had 172 variables, and reducing this is essential for optimization. To mitigate multicollinearity and reduce dimensionality, we engineered combined features. These new features, along with the dropped features, reduced our number of variables to 70 and reduced VIF scores to acceptable levels. You see here we created a total passing, total touchdowns allowed, total receiving, and a total rushing statistic. What this does is it takes, for example, total passing takes passing yards and passing touchdowns, and it combines them into one feature, so that way we keep the information of both variables while reducing our multicollinearity. You'll notice that we have some plus ones in here. Those plus ones are to help us distinguish between true zeros and low values for within each position group. For example, a quarterback could have thrown for 0 touchdowns and had 100 passing yards, and if we didn't have that plus 1, then that would result in a 0, which we believe would be misleading to our model. Alright, so let's analyze our total passing feature. We see that this feature is heavily skewed to the right with a significant amount of low values. These low values can be attributed to players who don't get much opportunity or are playing out of position. Some examples of this would be punters that threw a pass on a fake punt, running backs who threw a halfback pass. We also have backup quarterbacks that don't throw as many passes due to low opportunity. This feature shows how this emphasizes the importance of both passing yards and passing touchdowns. We see a very similar trend with total rushing and total receiving, as high performers are in a totally different league compared to the rest. This will be very helpful for our model to identify high-impact players. After our feature engineering, we ran a final correlation matrix that confirms that our new variables mitigated excessive collinearity while keeping powerful relationships between features. This makes the dataset much better suited for downstream modeling and analysis. So let's take a final walk through our dataset after feature engineering and dropping variables. I want to call out that we no longer have individual average draft position sources, as these are captured by average ADP. We also see that our total passing variable has replaced passing yards and passing touchdowns. Similarly, we see that our total rushing and total receiving features have replaced their related variables. I also want to call out that we no longer have individual field goals made broken down, as these are captured by total field goals made. Lastly, we also see that we have our total touchdowns allowed rather than rushing and passing touchdowns allowed.
In this slide, we'll be going over some of our next steps and further plans for the project. So in terms of initial modeling, we'll be training and evaluating models for fantasy point prediction, both for PPR and standard scoring. We'll be exploring XGBoost, neural network, and regression-based models, and we'll interpret those performances through metrics and feature importance and things like that to really refine the model. We may potentially adjust the pipeline using Windsorization for outliers and weighing seasons differently to prioritize a more recent player performance. So recent seasons will have a heavier weighting in the data and in the model. Then we'll move on to our recommender system development, where we'll utilize that initial modeling and really craft that personalized draft assistant that we're trying to build. And we'll also be incorporating custom draft logic like avoiding quarterbacks until the second round that kind of just follows the typical logic of a fantasy football draft. And then lastly, we'll be developing our dashboard that will be an interactive, customizable, real-time draft assistant user interface. Lastly, before we wrap up here, we just wanted to go over some key lessons we learned throughout this project. We learned a lot about recommender systems techniques and metrics, so matrix factorization for player recommendations, and accuracy versus serendipity, which is a little bit more novel in those recommendations, so utilizing those metrics. For data cleaning and handling missing data, we used a lot and learned a lot about regex-based disambiguation to standardize player names from different sources. We discussed true null values versus true zero values a little earlier. And we also really valued the quality assurance process of our data, going in, digging up the different data and making sure it makes sense. And lastly, for our feature engineering decision making, we learned a lot through our VIF score assessment. So using that variance inflation factor to assess multicollinearity in features, and then when it's best to combine versus outright drop different variables for the success of our systems. Thank you so much for listening and have a wonderful rest of your day. Thank you.